Today, we continue to work on our puzzle game using TypeScript and React. If you haven't seen previous episode, there is a link to the video in the description below. For now, let me go over what we have already done. I will remind you the rules of the puzzle game if you decided not to watch previous episode, and what was left unfinished. So first of all, we're playing on a small grid 4x4, where each cell represents either on or off states. On is represented by green, off represented by red. You can toggle any cell on the grid, and it will toggle all other cells which reside in the same row and in the same column. So for example, toggling this particular cell will result in all cells in this row and in this column be toggled as well. The win condition is to turn the whole board into green. We keep track of how many moves the player has made so far, and what we left unfinished is the actual counter, the optimal way of solving the board, the least amount of steps needed to solve the puzzle. Now, before we jump into the solver part, which will give us this information, I would like to make a few adjustments, a few small adjustments that will improve the UI just a tiny bit. So first of all, I noticed that our new game button, even though like clicking it looks nice, there is no cursor turning into pointer the same way as it does on our cell. So let's fix that. This is pretty much it. New game is now showing pointer cursor. Finally, these two boxes here in our game header, which are titles, I would like to first make them all uppercase. So text transform uppercase. Then we'll reduce the amount of space between moves and the counter. We can do it by saying that, hey, line height is just 1. Adjust the padding, say 5 pixels, and then we can update the font size to something like 23. And the only thing left is that this best box is somewhat narrower than moves, and we can adjust the minimum width to something like 60, and I believe it looks so much better. Now that this is done, we can start to work on our solver. Let's create a new file, solver.ts, and we will export a function named solve, which will take a grid as an input, and it will return a list of moves needed to solve this grid. Let's define some type aliases. Type grid is pretty much our 2D array of booleans, and type move is an object where we have row and column set. Right, so this says that give me a grid, and I will give you a list of moves where each move represents which cell to click in order to end up with the grid being solved. Now, the shortest solution usually requires us to use breadth first search, and that is exactly what we're going to do today. To implement it, let's use the standard array. Let's name some Q, which we're going to use to store current state with moves made so far. We're starting with push. We say that, hey, our current grid is grid, our moves are empty, so we haven't done any moves so far. We can then supply some type, let's say current state, something like that, type current state is going to be given grid at its current state and the moves that we made so far to reach this particular grid. Next, we have a while loop, which says that, hey, while the queue has some values, we do something, and because this puzzle always has a solution, we should end up finding it, and we should never actually move out of the while loop. So if we do, we should throw an error, so it is easier to understand that, hey, something went wrong, somehow we ended up quitting the while loop when we shouldn't. So yeah, puzzle should always have a solution. So what does the while loop do? It takes the next state to work on. So we can say, hey, the grid and moves is our first element in our queue or our array. Then we can drop that first value. And first thing that we need to check is whether we reached the final or winning state or not. So we can say that if has one grid, or maybe like not has one, like is one, we can say that, hey, here is the list of moves that actually transformed our initial grid into this current grid with the list of moves. Let's quickly define this is1 function, which takes grid as an input and returns boolean as an output. We can do it easily using grid every row. For every row there is a cell, and each cell needs to be true. All right, so if the grid isn't 1 yet, we need to toggle every single cell to transform the grid into the next state. Let's do that for let row from 0 up to our grid size. For each column from 0 to grid size. We're pretty much saying that, hey, like new grid is toggle cell given current grid, row and column. And toggle cell is a function that we already implemented. It is somewhere in game, so we can just add export here, and we can then import it and reuse it here. Now, once we generated a new grid, we need to verify that we haven't seen this grid before, because if you look at the grid and we toggle this top leftmost cell and we toggle it again, we end up in the same state as before, and we don't want that. We are pretty much interested in looking through all possible different states. To do that, we need to somehow check whether the grid has already been seen or not. To do that, we will have some visited set, and it is going to be a set of what? We cannot use grid here because grid is an object and it will compare by object references and they will never match. So we need to somehow transform our grid into some representation that the set will work well with. And we can convert the grid into a number. So given our initial grid, which came into the solve, we can say that, hey, like grid hash, this hash means the grid, and we can say that visited has seen this grid. I will show you how we can implement hash a bit later. Right now, let's get back into the main logic of while loop. So once we have toggled some cell, we have new grid. We need to say that, hey, I will have new grid hash as well. So hash new grid. And in case we haven't seen this new grid hash, which means that we have reached some new grid state which we haven't seen before. Then we can mark this grid as already seen one, right? And we can then push this new grid with new moves into our queue. And moves is going to be current set of moves, and we can cut a new move which say, hey, I simply need to toggle row and column. This is pretty much it for the solver. So we need to now implement this hashing. Let's see. So hash receives grid as input as well and returns some number. How can we do that? Pretty much our grid is 16 cells, and we can, every single cell has an index, so 0, 1, 2, 3, 4, 5 up to 15, and we can take a number 0, so let result 0, return result. This result is initially all bits are set to 0, and then we can go over each cell in our grid, and if the cell is on, is green, we can set the bit in this result to on as well. So we will use some bit manipulation on our numbers, and this should look like this. Once again, we go over all rows and all columns, and say that, okay, if the grid cell at this particular row and column is set, then we need to also set the bit in our result. We can use OR, so this is the same as equal result OR, just a shorthanded version, or 2 to the power of R times grid size plus C. Right? So again, if our result is initially all zeros, then first row is 0, column is 0, pretty much we end up with 0, right? So in this 2 to the power of 0 is pretty much just 1, or 2 to the power, yeah. Then our column changes to 1, 2, 3. Yeah. Once row is increased and column is reset, we have this multiplication. So when row is 1, we start with 4 plus 0. So it's going to be first 1, 2, 3, 4, 5, and so on. So this bit shifting is pretty much saying the same as result or math power 2 into the R grid size plus C. This should be equivalent here. All right, so this seems to be it, and we need to somehow integrate the solver into our game, or maybe game context. No, I think it's going to be game state. Let's see, let's keep some moves in our game state. So pretty much a list of moves, how to solve the initial grid optimally. Let's use grid. Let's move the aliases from this file to here. We can also export them so they can be reused in our solver. All right, so let's see, our initial game state, which was a simple constant, is now needs to be a function, because we first need to say that, hey, grid, please do initialize me a grid. then grid hash is, or not the grid hash, but moves is going to be like call our solve function with this grid, and then we can return the grid and the moves. So this is our initial game state. In game reducer now, we need to change, like whenever the new game is processed, we can say, all right, just initial game state, the function we just reworked. And finally, whenever we toggle a cell, we really don't do anything to the initial list of moves, so we can copy it over. All right. So if we refresh, our page doesn't work. It means there is still some errors somewhere. Game context maybe. Initial game state. It is now a function. Let's refresh. All right. So we can probably go to our game header component. In here we can say state, we can grab the moves and say moves length is exactly what we need. So it shows 6 here. So our solver said that, hey, you can solve this particular puzzle in 6 moves. I just click the cell and it's very slow. It is like really slow. So it seems that we are invoking the solve function every single time the component is redrawn. This happens in our context, I believe, like here, because that's where our solve is called. Right, so what can we do? We can probably say that game state is useMemo. So we memorize the result of initial game state. Right, initial game state as a function. No, it doesn't. Game state doesn't need that. Says unnecessary dependency. Okay. Let's see whether it helped us or not. Alright, so clicking the cells, it seems to be working fine as before. It shows us the best number of moves, optimal. Let's start. And here is the problem, is that whenever we click the new game, our solver is so slow that everything pretty much hangs for a few seconds. Again, new game, you can see that the button is pushed. It does some calculations. The counter is then shown and everything proceeds to work normally. Why does that happen? Pretty much it happens because every single time whenever we call solve, we do a lot of toggle cells function calls, and internally it does structured clone. So we have to go and do a lot of cloning, and that is very bad for our performance. So we need to somehow optimize our solver so that it works really fast, always pretty much, so that whenever even we click new game and solve is invoked, it will calculate everything quickly. So in other words, we need to drop or avoid using this structured clone somehow. As it turns out, the solution here is quite easy. We already know how to represent a grid as a number. And what we can do is that we can use the same number to actually to actually calculate new grid based on the number instead of using the grid itself. So we can see how that works. For example, we can drop the export for toggle cell. We cannot import that. So toggle cell doesn't work anymore. So our current state, instead of storing the grid, we will keep it as a number. We can say that it's going to be a grid hash, where grid hash is simply a number. This is simply for clarity, that we're keeping grid hash in our state instead of the whole grid. Let's see, we can calculate the grid hash in the beginning. We can say that, hey, our grid is actually grid hash. We are still keeping the same track of visited hashes. And then here grid is actually grid hash. We can say is1 grid. Is1 is now works with grid hash. So we cannot now go row by row and check every cell whether it's true or false. And pretty much because we have 16 bits, so 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4, we are interested in this binary representation of a number. So the grid is 1 when our grid hash equals to this value, and this value is pretty much 2 to the power of grid size times grid size minus 1. So we can say that, hey, like our win condition, or let's say like win hash, is 1 to the power of grid size times grid size minus 1. And then we can return whether the grid equals to our win hash. Alright, what can we do next is we need to define a new toggle cell which works not on the grid as in 2D array, but it works on grid hash. That is why we're gonna do it here, toggle cell. So given a grid hash, a row and a column, we will return new grid hash, or simply like grid representation as a number. And then we won't need to hash anything here. We can say that, hey, this is going to be visited new grid, new grid, new grid. So all that is remains is to somehow implement our toggle cell. And this is done by bit flipping. So let me show you how we can achieve that. So first of all, we need to once again iterate over all rows, iterate over all columns, and say that if row equals to R or column equals to C, we need to say that okay, first of all we need to say that new grid, we copy the grid value, we return the new grid, and now we can say that, hey, new grid is actually new grid, and we XOR the bit that we're interested in. So it's going to be R grid size plus C. What this thing does is that let's say we have some grid which is represented by something like that. We say that, all right, we're interested in this particular bit, which is represented by row and column. We use 2 to the power of this value, and we say that, hey, new grid, look at the bit in this particular position, and the XOR will make sure that the bit is flipped, because that's how like XOR table works. Let's see where it's some easy here. So if they are both zeros, well, we're not really interested in both zeros, because our x2, this second param here, is always 1, right? So if the bit in new grid is 0 and we XOR it with 1, we get 1, and if the bit is 1 and we XOR it with 1, we get 0. So this is pretty much bit flipping. And let's see, currently, at least it already shows the best value here in the new game. It does things very quickly. The only thing is that we don't know whether this solver, our new solver, is calculating things correctly or not. Right, so this particular value, the best, the optimal, the shortest amount of moves to solve the puzzle, is kind of useless right now. We can definitely compare the number of moves we made to it, but it would be better if we could somehow show, let's say, below the grid, show the moves that the solver produced. And one more thing is that whenever we click on the cells, we don't necessarily end up with the solution closer to the final win condition. It can actually, let's say at this particular point we have, let's say the game, it says that there are 9 moves to solve it, but if we click the cell, it can actually say that, hey, now there are 10 moves. So it would be nice if we could show not one number, not a single number, but 2 numbers, saying that, hey, here is the best or optimal number of moves to solve initial puzzle, right? The one you see during the new game. And another value which shows the optimal number of moves for current board state. That would be nice. So let's try to do that. First of all, I think we need to change the game state a bit. It would also be nice if we could reset the board to the initial grid. So let's say you solve the puzzle, it takes you, let's say, 15 moves, and the best is 10. And you would like to have another attempt or see how the solver solves the puzzle. So you can not only start the new game, which generates a new board, but you can reset the board to what it was initially. To do that, we probably need to change our game state a bit. So this is going to be initial and current, right? So we will keep track of initial grid, the one you get after pressing new game, and the current grid is once you click a few cells, this is current grid. This is going to be its representation. Then we'll have let's say some solver property, which says, all right, so here's a list of moves that solve the initial grid, and here is the list of moves that solve the current grid. We can drop that. Let's see, what do we need to update? First of all, initial game state, right? We say that grid is now initial it's grid, and current, it's also grid. And because these are objects, we need to clone so that we don't end up doing something to one value and adjusting the second just because they are stored by reference. Solver is also some initial moves and current moves as well. And this is also needs to be cloned as far as I can tell. Next, what else do we need to update? So whenever we toggle a cell, let's see. So new grid, we need to toggle current grid, right? So we're toggling the cell in our current grid. We need to update here moves. It's going to be solver. So initial is something, current is something. These two values can go here. So initial, it doesn't change, so we can simply say state grid initial. So this value doesn't change like ever until you press the new game button. But current is actually new grid. For solver, it should be the same situation here, something like state solver initial, which doesn't change much. But for current, we need some moves, and moves is probably solve new grid. Right, so we run this solve for new grid after every single move is made. This should be it. And now something breaks inside our components, probably game field. We need to work on current grid. What else? What else? Header. It says moves. All right, I think we need to go solver. So the best. All right, as I told you, let's do two things here. So let's show it this way. First value will be the amount of moves, the optimal amount of moves, the shortest length, the shortest path to the solution for current grid state. It means solver current length. And the second one is for initial grid. So solver initial length. Right? So whenever we start a new game, these two values should be the same. But as soon as I start clicking away, you can see that the first value changed. So I clicked something correctly, right? So number of moves became 8. If I click it again, right, it goes back to 9. And I have made already 2 moves. So I need to make 9 more, at least, to solve the puzzle. Right, let's see how it works. Let's say I'm gonna try and solve it. Yeah, so boom, and it shows 1, boom, we won. Now at this particular stage, when the overlay is shown, we would like to show like some reset button. Let's do that. I think that's game field. So it has 1. We need to show 2 things here. Let's do this. Let's do this as some paragraph probably, and a button which says reset game. Now we need to change our CSS. Let's see, this is game field CSS. This is win overlay we're talking about. So display flex, flex direction is probably column, right? So new game is shown below. And we would like our reset game to look the same way as new game does. New game comes from game info. There is a button, and we want pretty much all buttons to look the same, so we can move this out into some index CSS probably. We can say, hey, all buttons look the same. All right, the only difference here is that in Win overlay, our button, it should have some padding. So 15. I think that's too much. No, 10, 15. Yeah, something like that. And then, whenever we click it, it actually doesn't work. Why? Because we have pointer events none. We can move it to our paragraph instead of the whole thingy. So now it works, but it doesn't have any on click. So let's add that. Game field. We need to say that, hey, on click. We can reset game. Reset game will come from context. Reset game. It means that we need to go to game context. First we need to go to game and set that, hey, we have a new action which has type reset game. Our game reducer needs to be updated as well. So case reset game. What do? We return a state where grid initial and current. Then there is a solver initial and current, and then there is moves count. We reset to 0, has 1, reset to false. Grid is going to be state grid initial, and current is also state grid initial. So we are resetting to what our new game generated before. And once again, we need to do a structured clone here. Solver has already solved this initial for us before. It means we can say state solver initial. Same here because the grid is the same. And again, we need to do structured clone. Nice. What else? We need game context. We need to say that, hey, we need to have another helper reset game void. Then reset game should be here. We can reuse new game, change the reset game and say that, hey, type is reset game. And this is pretty much it, right? Let's see. So some new game. Okay, best 4. I don't know like how to solve it in 4. Let's see. If we go something like this, and then click these things over. All right. So we won. We reset. And it went to the same as before. So this thing is working now. So that's great. So you can now play around, solve it somehow, hopefully, right? And then once it's solved, you can say that, hey, I want to try it again. So you reset it back to the same state. Nice. So the only thing that's left is that we want to make sure that our solver produces correct moves. So we want to show them, and let's show them below our main grid. How do we do that? We need to go to our main component app. Let's say, yeah, some game solution, doesn't matter. we create game solution component, we probably will need game solution CSS as well. As usual, export const game solution. It's gonna be function component without any props. It will return some div game solution. Div, we go to app component, import game solution, and it's right here. Let's think what we want to have here. Let's give it an ID, game solution. This is going to be like some container, game solution, maybe container. Then we will have div with ID game solution. We need this to be like a container so that it can center the solution. Then we need to draw the grid again. Let's do it this way, like array grid size. We fill it with nulls. We map it. Bam, bam. This. It's gonna say div class name. Let's say like solution row. Div closes, and then again array grid size, fill null, map, and we say div class name is solution cell. Yeah, and we don't need anything inside of it, so we can close that. Right, let's see what we are missing. Is probably some key. Right, so solution row and some row index, which we can take from here, index. This div needs also a key, which is going to be solution cell. It's going to be using row index and cell index as before. We can take it from here. Cell index. All right. So this thing must be present in our DOM tree. Let's see. Game solution container has game solution, and here they are. Right, 4x4. It's just we don't see them yet. So let's open up our CSS. Let's say game solution container. Then underneath it we have game solution. Then inside of it we have some solution row, and inside of it we have some solution cell, something like that. So the cells will be somewhat small. Let's say something like 30 pixels probably. Right? That's let's say border 1 pixel, solid red for now. Nothing is shown, fine. Let's say we display it as flex. Why is nothing is shown? It's because game solution, we need to import game solution CSS. Right. So right now we can see all the cells. We can say that hey, our game solution is going to be flex, and it should use the direction of row. Nice. This one should align items center, which no justify content center. Yep. And then it can use some margin top. Okie dokie. So row, each row like also display flex direction is column, and we need some gaps as usual. So cell margin right 6 pixels and last child doesn't need margin, right? Cool. The rows margin bottom in the last child also doesn't need margin bottom. Did I make a mistake somewhere? Why doesn't it show my margins? The row. Why? What is wrong? What is wrong? Margin top. Wait. Solution row. It does jump, right? Or it doesn't? No, it doesn't. What is going on? Let's see. Game solution T6. Solution row, class name. Yeah, should be fine. So some error in here. I would like to add a gap between the rows. These cells worked fine. Margin bottom 6. Like 16 doesn't do anything. What did we do wrong here? Div. This one's closed. Solution row. Game solution. What is up? Can I border 1 pixel solid green? Let's drop the red one. Of course. Row. My god, such a stupid mistake. All right, so this one's it should be column. Nice, finally. Let's bring back the border here. Pixel solid red for now. Nice and nice, something like that. 0 pixels. Oh, yeah, even just 0. All right, so we need to style it a bit more. I don't want to bring in colors here. I will probably just show it in a somewhat grayish. Let's see, like cell can be background, something like RGBA, 100, 0.3. Yeah, border can be solid RGBA of something a bit darker, like 120, 120, 120, and maybe a bit like 0.4, something like that. We can also reduce opacity on the whole container. Yeah, this looks a bit nicer. And now we need to go back to our component, and we need to somehow mark the cell that is next in line in our solver moves list. So first of all, we need to use our useGame hook, right? So XXX. So let's break it down. We need a solver, right? So whenever we reach a cell, we need to check. So is next move. Is next move, then we add another property like next move, otherwise some empty. So what is next move? So pretty much our solver current, is it? What is solver? No, not any. So it has to be state, and there is a solver inside state. Yep. So solver current solver current 0. Solver current list of moves. So it needs to take a, yeah, we need to say next move is actually solver current 0. If not next move, we can return null, and this can happen whenever we have already solved the puzzle, so there are no next moves. And then here we can say that, hey, if next move row equals to row index and next move column equals to cell index, then we can add the next move. Let's see whether that applied to our small solution grid. We have bam, 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 cell, 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 cell. Where is next move? Only one of them has it. So we need to only style it. So solution cell, probably need to tell solution cell next move. How do we want to style it? We probably want to say that, hey, my background is going to be like darker, my border is going to be darker as well, probably something like 20, 20, 20, a bit more opaque. This is going to be like something like 30, 30, 30, yeah, and we can probably say that filter blur, something like that, maybe even like some box shadow. I think we can do something like 0, 0, 4, and then I don't know, something like that. So it's a bit like blurry. Yeah. So currently this solution board shows us the next move that we need to clickety-click to proceed with the solution. As an exercise to you, you can integrate or create some toggle here to either show or hide the solution board. For now it's always shown. So all we need to do is check whether the solution actually works. So let's try to follow it. It says 11 moves to solve the board. Let's start. Nice. It's actually and yeah, 11 moves, and 11 moves was as our solver set. We can reset the game, same state, same solution, which is really great, really nice. So this pretty much concludes this project, which now has a fully functional game. We have a solver and we have a overlay that shows the solutions that you can either use or not. If you like this project, like this video, I kindly ask you to like the video, and if you want to be notified about future projects, please do subscribe to my channel. Thank you very much. Bye.